Hi, my name is Rich Conant, and I'm a professor of ecosystem science and sustainability at Colorado State University. And it's nice to have the opportunity to participate. And this issue of carbon cycling and grazing lands is something that I've been working on for a few years, and I find very interesting. And it's an issue that's gotten a lot of attention recently, and so I'm happy to take the opportunity to share my thoughts with the group. The first part of my talk is going to be focused on what we know about grazing lands. And we know quite a bit about how grazing land carbon cycles happen and how we can influence them. The focus of my research is on soil biogeochemistry. But of course, soil biogeochemistry is influenced by what happens at the surface, and carbon flows into plants through vegetation, and then some of that carbon is transmitted below ground through allocation or the death of above ground material. And some of that carbon that flows below ground in turns becomes soil carbon. Some of it stabilized for a long time. Some of it respired back to the atmosphere fairly quickly. And of course, some of the above ground carbon can be taken up by grazing animals as forage and then returned to the atmosphere via respiration. And the primary drivers of these fluxes are climate, which of course influences the productivity of vegetation and the allocation below ground and the types of allocation below ground and the decomposition rate of both surface organic material and organic material that's deposited below ground. Soil characteristics can have an influence on both above ground productivity and stabilization of carbon. And of course, fire frequency and past land use have an impact on ecosystem carbon stocks as well. And the things that we do on the land have a big impact on how much carbon can accumulate in the soil. And the things that we do can include different aspects of grazing intensity and seasonality. There are things that we can do to affect the species composition, either directly through sowing species or removing species, but also indirectly as a function of grazing management. And we can have a big impact on soil fertility as well through our influence of grazing animals, but also directly interventions on soil fertility. And we have tools now that can do a pretty good job of predicting soil carbon stocks for a given place, and can do okay with predicting gains and losses that might be realized with changes in these aspects of ecosystem management. And one of the main reason this has gotten so much attention beyond those interested in management of grazing lands alone is for the system carbon changes. And typically the way we understand this is that, given consistent management interventions, we might expect to see that ecosystem carbon stocks reach some equilibrium between inputs and outputs, and so are reach some steady state over time. But given some intervention, like tillage, for example, is the classic example, but in grazing systems could also include things like overgrazing, we might see a depletion in soil carbon stocks. And given consistent management, we might expect that those interventions will lead to some new steady state that's lower than it had been in the past. But then if those systems undergo some kind of management change, we might expect to see that there could be a gain in soil carbon stocks that might approach what was present in the native systems, but in some cases could exceed what was present in those native systems. And again, this has gotten so much attention because we have this severe problem of increasing CO2 concentrations in the atmosphere, and there is a huge flux of carbon into and out of the land every year. Grazing lands cover a large fraction of the Earth's surface, and so it feels like interventions could have an effect on that flow of carbon into and out of grassland ecosystems that could increase the carbon balance of those systems, effectively drawing CO2 out of the atmosphere and storing it primarily in soil organic matter in grazing systems, but also in vegetation. And this is true. We've looked at the literature on this, and we've documented, this is data from a paper we published in 2017. We have an earlier paper that did the same thing in 2001, and the results were fairly consistent. There are lots of different practices that people can use to change the carbon balance of those systems, and those practices include things like fertilization that might only be introduced in places where we have enough precipitation to see a benefit, a yield benefit for fertilization. They also include things like grazing practices that can be implemented on any land, any grassland where there are grazers. And on average, these practices, when we compare what's characterized as improved management, which often is associated with improvements in forage productivity, we see a gain in carbon stocks in comparison with an unimproved management practice across all of these. And again, these data were consistent in the review that we did in 2001 based on publications before 2001, and this review we did in 2017 with papers that were published since 2001, or not included in that first review. And if we're focused on rangelands, the intervention that we can that is required of using those lands for grazing is thinking about the grazing management and improving the way that those systems are grazed. And grazing management, we think, can reasonably lead to increases in soil carbon on the order of something like 0.2 or 0.3 tons of carbon per hectare per year. Note that those are tons of carbon per hectare per year, not tons of carbon dioxide per hectare per year, which is the unit that's usually used within the carbon markets. And how do we do this? How can we manipulate grazing management in ways that might affect the flow of carbon? There's the potential that that grazing management could improve the photosynthetic capacity of ecosystems. It might alter allocation patterns. There are ways that grazing might be expected to increase allocation below ground that could lead to increases in soil carbon stocks. It might increase the proportion of fast-growing plant tissue. For example, if rotational grazing might lead to keeping the plants that are growing there at an earlier growth stage, which some people think might be faster. All those things can lead to potentially positive benefits. Some could lead to negative benefits too if they're misapplied. And then there might be ways that changes in species composition could alter carbon flows too. It might be possible to seed new plants that have an impact on allocation patterns. It might be possible that grazing management could have an impact on species composition that's manifest in allocation patterns. For example, here in the shortgrass steppe near Colorado State University, it's been well documented that in the absence of grazing, there's a strong preference for C3 species that have less below ground allocation, and that could lead to reduced carbon inputs below ground and loss of soil carbon over time. Changes in species composition could also increase productivity, and it might be a general change in productivity. It might be a change in productivity that's only manifest during dry years. Again, here on the shortgrass steppe, those C3 species might be adept at growing productively during wet years, but they're less adapted to dry years. And so we might see a significant increase in production under certain conditions, certain years, that might be mirrored with reductions in production during dry years. And this could also alter the standing stock of vegetation, and this becomes particularly important when we talk about practices that affect the amount of carbon in woody biomass. Overgrazing, changing fire regimes, CO2 fertilization might lead to changes in species composition, might all contribute to changes in species composition that lead to carbon accumulation in above ground and below ground biomass. The numbers that people talk about when we think about encouraging practices that lead to increased carbon stocks in ecosystems are substantial. Added up around the globe, they're comparable with what you might expect to see with carbon storage in the world's croplands. So pretty substantial and certainly worth considering because again, this challenge we face in drawing CO2 out of the atmosphere. Right now, we've got limited tools at our disposal, and so I believe that we need to use every piece of ammunition that we've got as effectively as we can. So the numbers in grazing lands are potentially substantial, technically. But how much of that technical potential is realistic that's a different question, and we've done some work to try to assess that, and the work that we've done maybe has been more restrictive than some other pieces that have attempted to address questions about practically what might we be able to achieve in the world's grazing lands. And I'll summarize a couple papers here. One is this paper by Henderson and all that was published in 2015. And then in that paper, we took an approach where we thought that we would identify carbon storage potential in areas where an improved practice could also lead to improved forage productivity. And so this means this is very restrictive. We can imagine all kinds of cases in which a reduction in forage production or a reduction in utilized or utilizable forage could lead to increased carbon storage. But really, grazing lands are used for grazing, and we went into our assessment with that as a first constraint, that we didn't want to, not only did we not want to reduce forage consumption in grazing lands, but we wanted to focus on places where management intervention could have this win-win, where we would see an increase in forage production and an increase in carbon storage. And we focused on a few different practices around the world. We focused on native grazing lands. We focused on grazing and in planted pastures. We included grazing management practices and also the practice of sowing legumes, which is in many places economically beneficial, a way to improve soil fertility. And but it does come with some nitrous oxide increases. And so further constraint that we had in our work was to only account for cases in which we saw a net carbon benefit. In other words, the carbon storage gains offset the increase in nitrous oxide fluxes attributable to increased soil fertility. And so what you see here is a really more constrained estimate of the carbon storage potential in grazing lands. And our work, our results differ quite a lot from that technical potential, which doesn't include any of these constraints. And you can see the distribution across these different practices in different parts of the world and different types of grazing systems in this figure. And these data were used in this cites this. This is actually a paper by Griscom et al., Natural Climate Solutions, a famous paper that's received a lot of attention. And we essentially rolled up our estimates for realizable carbon storage in grazing lands as part of this larger effort to characterize natural climate solutions and carbon storage or emission reduction potential in the world's ecosystems as part of a nature conservancy effort. And you can see that the numbers here for grazing systems are quite a bit smaller than those IPCC comparisons, because again, we had these constraints in our study that limited our geographic scope and limited where those practices could be implemented based on whether they resulted in a forage gain. Whether you think those were reasonable or not is certainly a question worth discussing, but that's why our numbers up here are smaller here in this work. But it's still clear that globally that there's substantial storage potential in the world's grazing lands, and I believe that we ought to do what we can to realize those carbon drawdowns, because the cost of reducing these emissions is quite low. Again, because we constrained our estimates to conditions in which we'd see a gain in forage productivity. So you've got this built-in incentive for people to adopt these practices. So in summary, what do we know about carbon fluxes in grassland systems? We know that carbon stocks, soil carbon stocks in particular, are substantial. We know that the things that we do on the land can have an impact on those carbon fluxes and can lead to loss of carbon, but that a lot of that carbon can be regained, and we might even gain more carbon than was present in the native systems. So we can increase carbon storage in our ecosystems, and that the technical potential to do so is quite large. The economic potential to do so, or the potential that we think is more realistic, is quite a bit reduced from that large technical potential, but still substantial. So now the second half of my talk, what don't we know? What do we still need to improve our learning about? Um, One of the challenges that we have is that data on the ground still remains sparse. There's a growing body of literature, and the fact that we're able to repeat a review in 2017 that we had just done, 15 years before, and that we found more literature in that 15-year period than we had in every year that preceded 2001 suggests that this is an area of growing interest. We're getting more data, but there's still a little consistency between sources. It's a real challenge to synthesize data. The experimental contexts vary quite a bit, and there's quite a bit of variability in how grazing systems respond to changes in management. So lots of uncertainty, and this is a problem because some of the cases in which we see, really significant potential for carbon gain are from a small number of studies, and it's difficult sometimes to understand the conditions that lead to those observations in some cases, but not in others. Experiments aren't evenly distributed either. This has improved since our 2001 paper, but there's quite a bit of bias in where those studies are done, unsurprisingly. Another problem is that the way in which these observations are collected. Typically, we're in a situation where the now is now, and we want to know what the future might look like. But the way we do that is based on sampling what has happened in the past. Ideally, we would be able to sample now and sample in the future and gather some information. But practically, the way that people have tackled this challenge is to sample a variety of different management practices now and look back to what things we think were like in the past using one of those samples. And this, of course, requires the assumption that what we can observe now is like what we observed in the past. And we know that this isn't always the case. So this really contributes to our uncertainty about these studies, the fact that we're constrained and that we really want to have information now rather than set up experiments that will tell us at some time in the future what that future looks like. And this is compounded by the fact that in grazing systems, these changes happen pretty slowly. And so we can't afford to wait for this information. And so what this means is that typically we're making this assumption about how representative a field that we sample now is of what other fields looked like in the past. So we're doing this space for time substitution. And and most of the data that we have is from these kind of across the fence comparisons. And so that's inherently unsatisfying because of these assumptions that go into this kind of work. I think it limits our confidence in these results. So this contributes to our uncertainty in these studies. And we have a bunch of outliers that seem uncertain. Another challenge that we face is that the tools that we have for assessing and making predictions about what might happen in the future are limited too. This figure shows some work that we've done based on this compilation of grazing studies, and we were able to model, given the data in the paper, we were able to model some of those studies, and we can do a pretty good job of modeling the soil organic matter content across all those studies. You see the R squared, you're 0.98. That's awesome. But that's across space. It's not across management practices. And the models do much less well at representing the response within a site to changes in grazing management practices. And so this figure shows for a particular site how well the measured and the model correspond to each other. And you can see that we're not able to explain that variability very well at all when it comes to looking at different grazing studies. And there's bias too. And so what this means is that we have tools that are good at telling us how much carbon we expect to see in a given place, given those larger drivers for soil carbon stocks, climate, native vegetation, and soil characteristics, but we're less good at representing changes that you might expect within a site given a change in grazing management practice. And that's a real problem because people aren't interested in right now in tools that will help us characterize carbon in some unknown place They're interested in tools that will help us understand if we change our management practices, how much will that change soil carbon stocks. So our tools need to catch up with demand for that information. And I think that we can get there. I think that it's going to take a concerted, systematic effort of scientists attending this conference and others to improve how well those tools represent these practices, to continue to collect information that will allow us to understand what's driving those processes, and to integrate those data together in a way that we can use them to improve our models. Finally, we don't really have much good information at all about how widely practices are that can sequester carbon, and where the opportunities are to improve practices. I know that here, this difference between technical potential and realizable potential is a function of the current state of the grasslands. If all grasslands are optimally managed, then the scope for carbon sequestration is quite limited. But if all grasslands are overgrazed, which we know is not true, but if that were the case, then there would be oodles of potential. We just really don't have good information about the current status of grazing management that allows us with confidence to extrapolate how much carbon might be stored. And activity data are really hard to come by, and so it's hard to know exactly the way the situation is now, and that's true across much of the world. You'll remember that figure I showed earlier that showed the trajectories of ecosystem carbon over time. If we're at a low spot, there's lots of potential for gain. If we're at a high spot, the potential for gain is much smaller. And we just, in a lot of places, a lot of times we just don't know where we are. And furthermore, it's hard to discern from the literature where we are in that curve. And so we've done our best to characterize the difference between improved grazing management and alternatives, but it's hard to understand exactly where those rate on that scale of these soil carbon trajectories. So with that, I'll conclude, and I'll look forward to the panel discussion. I hope that you've learned a little bit about my perspective on carbon cycling in soils and the challenges that face us. I am optimistic that carbon storage in grazing lands has a role to play in our drawdown of CO2 concentrations. I think that we need to use every piece of ammunition that we've got to attack this problem. I remain optimistic too that the tools that we have will evolve and improve. What the tools that we use now weren't created to do this, but now there's a huge growing demand for this kind of information, and I'm optimistic that the science will respond. Thank you for your attention.